Hello everybody. Let's start. Firstly, I'm going to discuss the maximum and minimum of a function. Generally, whenever this question is asked to you all, most of the time you give the answer in the fashion that when the derivative of a function becomes is equal to zero, then at such point the corresponding point is called the maximum value or minimum value. Like this, generally we have a function, this kind of function. Hmm. Maybe these are the two coordinate axes. Say this is our x-axis and this is our y-axis. Hmm. The function may have this kind of nature, may have different kind of nature as well. Now, generally, you answer the question in this fashion that whenever the function has the derivative equal to zero, at that point the function is said to have a maximum value or minimum value. But that is not the definition, because there are certain functions, like you see over here, this kind of function. There are certain functions as well. At this kind of point, hmm, you can check that the function is not differentiable at all. Okay, this kind of points has maximum value, but we need the definition, a proper definition of maximum. Probably it has been discussed in your class 11 and 12 level standard, but for a recapitulation, as I am just going discussing this one. Hmm. And if anybody has any misconception, they may clear this misconception through this definition. So what is the maximum value? The maximum value of a function or minimum value of a function, both of these are actually relative values. You see, actually it seems that maybe at this point, suppose C, this is suppose C point, okay, and at this point it seems that the function has the maximum value at the point C. If this is the let us suppose that f is the function, then we can say that f has the maximum value at the point C. And what is the maximum value? This f of C, this is the maximum value of the function. But maximum value is actually defined with respect to certain small neighborhood. What is this? It says that if we have a sufficiently small neighborhood of a particular point C, then within this neighborhood you will find the nature that if you consider any arbitrary point. It is not much bright, the color is not much bright. Yes, hopefully this one. No, not this one. uh, Maybe this one. Yes, if you consider any arbitrary point x, maybe this is the position of the arbitrary point x. Okay, if you consider any arbitrary point x in between, within a sufficiently small neighborhood of the point C, and this value is equal to f of x, this much height is equal to f of x. Got it? And if this f of x is less than or is equal to f of c for all x within this neighborhood, then we say that the function has maximum at the point x is equal to c. I am repeating this definition again. If by chance this f of x is less than or is equal to f of c at each and every point x within this neighborhood, if this f of x is less than f of c, then we say that the function f has maximum value at the point x is equal to c. And you see the same definition is true for this kind of function as well. Say at this point maybe at this point the function has a maximum value at the point C, and consider a sufficiently small neighborhood of the point C, and say this is the value, this is the position of x, then this would be our f of x. Okay, and you see over here this f of x is less than or is equal to f of c. Therefore, although the function is not differentiable at the point c, therefore we can say that f of x is less than or is equal to f of c for all x. Minded, this result should be true for all x within this neighborhood, for all x within this neighborhood of the point c. Got it? If we have at least one point x which does not satisfy this inequality, then we cannot say that the function f has a maximum value at the point c. Alright. So this is the definition of maxima at the point C, and similarly if we have opposite kind of inequality, that means if the curve may have this kind of shape or may have this kind of shape, in that case we will have this kind of inequality that f of x, this f of x should be greater than or is equal to f of c. Okay, this f of x should be greater than or is equal to f of c for all x belonging to that neighborhood. In such case, we say that the function f has a minimum value at the point x is equal to c. So these are actually definitions of maximum and minima of a function. And now I am going to I am going to discuss two results related to this maximum and minimum. Let f has a maximum value or minimum value at x is equal to c. Okay. Then of course we can write that if the function is differentiable, then we can write that f dash c is equal to 0, dy dx or f dash at the point c must be equal to 0. Now the question is that how to determine whether the function f has a maximum or minimum at the point x is equal to c. This is a necessary condition. If we have a maximum, then f dash c is equal to 0. If we have a minimum value, then f dash c is equal to 0, provided the function is differentiable at the point x is equal to c. Now we suppose that the function is has sufficient differentiability, and if we now need to confirm that whether that the function has maximum at the point x is equal to c, then you got a result in your class 11 and 12 level that in that case f double dash, the double derivative f double dash at the point c should be less than 0. Got it? That is the condition under which you generally conclude that the function f has a maximum value at the point c. Then you generally conclude that f has a maximum value at x is equal to c. Maximum is, remember, this maximum or minimum are always defined relative to the neighborhood. So these are all relative maximum or minimum. I am discussing only the relative maximum and minimum. Okay. Although we write simply maximum, but we are always discussing. We shall always discuss this relative maximum and minimum over here. And similarly, if suppose we have the result that f dash c, f dash c is greater than 0. Okay, if suppose we have the result that f dash c is greater than 0, then we write that f has minimum value at the point x is equal to c. Now, what would happen if f double dash c becomes is equal to 0? Let me give you an example. Suppose f of x is equal to, that means y is equal to, of course, y is equal to f of x, and that is equal to x to the power of 4. Okay. And if we draw the graph of this function y is equal to x to the power of 4, let me draw the graph over here. Plot the function, rectangular plot. This would be the graph of the function. Let me minimize this one a bit. Yes, this would be the graph of the function. Starting from, say, over here, it plots from minus 5 to plus 5, and at the point x is equal to 0, you see the graph, it appears that the graph is minimum at the point x is equal to 0. But still, if you consider the derivative over here, f of x is equal to x to the power of 4, then it means that f dash x is equal to 4x cube, and f double dash x is equal to 12x square. Okay, and in such case, f double dash at the point 0 is equal to 0. But still, the function has an extreme has the minimum value at the point x is equal to 0. We expected that if the function has a minimum value at certain point over here at the point x is equal to 0, we expected that this minimum value, the f double dash, at that point, particularly at that point, would be greater than 0 if the function has a minimum value. But over here we are getting equal to 0. So in such cases, what to do? All right. Whether the function has any extremum or maximum or minimum value at all, that we need to confirm. And I am giving you one more example. Suppose I am considering a function, the second example over here, I am considering a function fx is equal to x cube. Now if we again draw the curve, let me draw the curve. This would be the curve of the function x cube. This is the curve of the function x cube, and you see at the point 0, on the left of the at the left neighborhood of the point x is equal to 0, the function is negative, and on the right neighborhood the function is positive. So it does not have any extreme value at all at the point x is equal to 0. So in this function as well, in this kind of function as well, if you consider f dash x, that would be is equal to 3x square, and if you consider f double dash x, that would be is equal to 6x. But in both of these two cases, f double dash at the point 0 becomes is equal to 0. So over here I am considering two examples. One is the example for x to the power of 4, and this is the graph of the function x to the power of 4, and for this function the double derivative becomes is equal to 0, and this is a function of x cube. This is the graph of the function x cube, and over here it does not have any minimum value or maximum value at the point 0, but still over here if double dash at that particular point 0 or c, this f double dash becomes is equal to. Now how to conclude whether the function has any maximum value or minimum value at all? It may have any maximum or minimum value, it may not have any maximum or minimum value. Okay, so I am trying to make your concept clear, how to get a certain definite conclusive result. I am not going to prove all these results. I am just stating the results only, the statements of those results. In such cases, whenever the double derivative becomes is equal to 0, from these two examples, it is clear that it would be very difficult to make any conclusion at all. We can say the case should be studied further, or it is undecided in this level. The case remains undecided in this level. But how to obtain a decision on this kind of functions? In such cases, what we do, we try to differentiate the function as many times as possible until and unless we get a non-zero derivative at that particular point under study. Over here, the point under study is x is equal to 0. Okay. So you see, we shall try to differentiate the function as many times as possible until and unless we get a non-vanishing derivative. And if the order of the first non-vanishing derivative becomes an even number, in that case we can have certain definite conclusion. But if it is odd number, then we can say that the function does not have any extreme value at all. Let me show you by these two examples. Over here, fx is equal to x to the power of 4. Let me first consider this example of x to the power of 4. Y is equal to x to the power of 4. We got the result f double dash. Let me copy all these results. We have the result f double dash at the point x is equal to 12x square, and it gives us that f double dash 0 is equal to 0. Fine. Then what we need to do in this level after as because in this level the case is undecided, what we should do, we shall continue the derivative process as because it's a polynomial, so differentiation is permissible. So we find the third derivative f triple dash x. F triple dash x is equal to, it would be 24x. Still you see, f triple dash x at the point 0, f triple dash x at the point x is equal to 0, this should be is equal to 0. But we are not getting any non-vanishing derivative. Then what to do? We shall again consider fourth derivative. I am writing in this fashion, f for x, fourth derivative should be is equal to 24. So first non-vanishing derivative, order of that non-vanishing derivative is equal to 4. Over here, the derivative order of the derivative order is equal to 4. Order of the first non-vanishing derivative is equal to 4, and it is an even number. It is an even number, and therefore, as because it is an even number, we can now make definite conclusion regarding its maximum value or minimum value. How to make conclusion? Over here, if the if this first non-vanishing derivative is negative, then it would have a maximum value, and if it is positive, then it would have the minimum value. Okay. Over here, the order of this first non-vanishing derivative is equal to 4. And what is the value of that derivative? Over here you can see, you can check, if you put x is equal to 0, you can, if you put x is equal to 0 over here, the value is again remains 24, and this is a positive number, so the conclusion is that x is equal to 0 is a point of minima. Okay, point of minimum value of x. X is equal to 0 would be a point of minimum value of x. But suppose if you consider this kind of example, in place of x to the power of 4, let me try to draw the graph of minus x to the power of 4, just a negative sign, and try to draw the curve of this function. In that case, this would be the curve. Let me minimize it a bit. Yes, this would be the curve of the function fx. And you see, look at this curve. it is clear that the function has maximum value at the point x is equal to 0. And in such cases, what to do? You see, in such cases, we can continue the process, and finally we will have fourth derivative, and that would be the first non-vanishing derivative, and that would be is equal to minus 24, and this is a negative value. Therefore, we should have a conclusion that if at x is equal to 0, the function has a maximum value at the point x is equal to 0. So this is the point of maximum. So if the first non-vanishing derivative, order of the first non-vanishing derivative is an even number, then we can definitely make conclusion about the maximum and minimum value of the function. Okay, if the first non-vanishing derivative is positive, then we would have minimum value, like in this first case for the function x to the power of 4. If we have a maximum value, if the function f the first non-vanishing derivative is negative, then the function would have a maximum value at that point, and in these two cases we can make definite conclusion. Now, how to make the conclusion that the function does not have any maximum or minimum value at all? And in such cases, uh, you see, if you consider this picture, the picture of the function x to the power of 4, sorry, x cube, not x to the power of 4. This is the picture of the function x to x cube. Let me copy this one, and now let me paste it over here. This is the function of this is the graph of the function y is equal to x cube. So this is the function f of x is equal to x cube, and clearly this function does not have any extreme value, neither maximum nor minimum. And in this kind of case, if you consider the first derivative, f dash x becomes is equal to 3x square, then f double dash x is equal to 6x, and f triple dash x is equal to 12. And if we want to study the point of extremum at the point x is equal to 0, you see over here f triple dash at the point 0, that is equal to 12. This would be the first non-vanishing derivative at the point x is equal to 0. Its previous order derivatives, all the previous order derivative, if you consider f double dash at the point 0, that should be is equal to 0, because f double dash x is equal to 6 of x. So if you put x is equal to 0 there, you would get that f double dash 0 is equal to 0. But over here, f triple dash 0 is equal to 12. So this is the first non-vanishing derivative of the function f. And what is the order of that non-vanishing derivative? Order is equal to 3, and 3 is an odd number. 3 is an odd number. So in such cases we will have to conclude, we will have to make the conclusion that, as because the order of first non-vanishing derivative is an odd number, so in such cases we can say that the function f does not have any extremum at the point under consideration, maybe at the point c is equal to, over here I am considering c is equal to 0. So in this way you can conclude that the function has maximum value or minimum value at all. Now, is it clear to you?
Yes, sir.
Okay. Now I am going to discuss one more technique by which you would be able to find out the maximum value or minimum value of a function. Because you see, as I told you earlier, that suppose f of x is equal to this kind of complicated function, say x minus 2 and suppose x minus 3 by x minus 4 and then x minus 5. Now the problem is that the function is so much complicated that differentiation of the function for the first time would be difficult, and for the second and third time it may be very much difficult. Without the help of any computational device, it would be very much or next to impossible job by hand to compute the second or higher order derivatives of this kind of function. Is it so? Because this is the first derivative would be very difficult, u by v like function. So the first derivative would be very difficult task, and you may have some patience so that you can find the first derivative. Hmm. Now let me find out the first derivative of the function. I have computer in my hand. Hmm. So I am going to compute this first derivative pdx of this function. Let me see if it is possible. Yes, thanks God to this computational device, and we can compute the first derivative over here, f dash x, as because I have this computer in my hand. So now over here the computation of first derivative becomes easier for me, but for you, if you by hand want to compute this derivative in exam, at least it may be a bit difficult task for you. Now if I tell you to compute the second and higher order derivative, that computation may be very much difficult, and in your exam most of the students would like to leave that question and rather attempt another question. And in such cases we have a easy technique by which we generally able to find out the extreme value. And let me discuss one example from book in page number 713, 713, from the book of Ghosh and Mighty. This is example 12.4.5, page number 713. Over here, if suppose we want to find out the root of this equation, then what would be the roots of this equation? These are the roots. Okay. So over here, suppose we have a function fx is equal to this, and this derivative f dash x would look like this. It's very complicated, and this f dash x would become is equal to 0 provided this numerator becomes is equal to 0, and when this numerator becomes is equal to 0, we have this type of solutions. Say x is equal to 3, x is equal to 7, x is equal to minus 2, x is equal to minus 1, and x is equal to 1. So we have we have six different solutions, or six different roots of this equation. Okay, and in such cases we expect that at maybe at certain point, maybe at the point 3 or 7 or 2, some maximum or minimum value may appear. Then what we shall do, we shall always try to first arrange these numbers or these possible values. This kind of values are called stationary values. We shall always try to arrange these possible values in increasing order. So I am trying to draw a table for you. So the first, the smallest value is equal to minus 2, and then minus 1, and minus 1, you see it is minus 1. After minus 2 we have minus 1, and then what we have, plus 1. So x is equal to 1 is the next immediate value, 1, and then x is equal to 3, and then x is equal to 7. Hmm? So we don't need this last. So out of this 5, what we shall do, we shall always try to look at the sign of this function. Hmm? How? Let me show you the picture once again. Let me clear this one. Okay. You see, suppose the function is this kind of function. Hmm? This is y-axis, this is x-axis. Okay. And suppose this is the first value, maybe x is equal to -2, then x is equal to +1, and so on. I'm not writing -2 like this. Maybe this is x is equal to -1, this is x is equal to -2, let me write it. And then what was the next value? The next value was sorry, the next value was 1, 3 and 7. Fine. The next value is 1, 3 and 7. So suppose this value is equal to 1, then maybe this is the value at the point 3 and maybe at the point 7. Hmm? And I'm not considering the further values. Now, you see, if you have any extreme value on the left of this kind of extreme value, on the left of this kind of extreme value, say this is the pointer at the maximum value. On the left of this kind of maximum value, if we consider a tangent line, this kind of tangent line, and we know the slope of the tangent over here, what is the slope of the tangent? This angle would be the slope of the tangent. This angle is less than 90 degree. Got it? So tan theta or dy dx or tan theta, dy dx or tan theta, as because theta is less than 90 degree greater than 0, therefore this tan theta should be greater than 0 on left side. Okay. And if we draw a tangent on the right hand side, in that case, this value of dy dx, you see, the slope of the tangent would be is equal to, over here the slope of the tangent is this kind of angle, and this angle is greater than 90 degree and less than 180 degree, and in that case tan of theta would be less than 0. Hmm? And therefore this dy dx would be less than 0. So the conclusion is that if we have a maximum value and we just change the value of the variable x from left to right through this point under consideration, hmm, the point which is under study. Okay. As we change the value of x from left to right, or as we increase the value of x from left to right through this point under study, and if the derivative changes from negative to positive, okay, in that case we will have a maximum value. And if converse result comes over here, suppose you don't consider this kind of point, suppose at this point, hmm, at this kind of point, at this kind of point, say this is the point C, suppose, and now if we increase the value of x, if we increase the value of x through this point under study, then you see on the left the tangent is like this, hmm, and therefore the angle would be greater than, this angle would be greater than 90 degree, less than 180 degree. So tan of theta should be dy dx, this dy dx should be less than 0. Okay. And if we draw a tangent on left, on the right side, at this kind of point, if we draw a tangent, you will see that this angle, now this angle is greater than 0 and less than 90 degree. and therefore in that case tan theta or dy dx should be greater than 0. So if suppose at certain point as x increases through the point C, in such cases if dy dx changes its sign from negative to positive, initially it was negative and now it is positive. Okay, if dy dx changes its sign from negative to positive, in that case we will have a minimum value as I demonstrated over here. Now is it clear to you?
Yes, sir.
Yes, sir.
Now this can be, I'm just going through this exercise and looking at my book. This numerator, if you look at this expression, this numerator can be written as 72 into x plus 5, then x plus 2, then actually probably I missed the solution. X is equal to minus 5. I don't know. Maybe some 1, 2, 3, 4, 5. Yes, one solution is deleted by chance. I don't know why. Hmm. So let me insert one column on the left position. It should be minus 5. Hmm. So x plus 5, x plus 2, then x plus 1. Okay, then x minus 1, x minus 3, and then x minus 7. So this would be the factor, and we will have one more solution like x is equal to minus 4. So forget about it. From this factor it is clear that the solutions are x is equal to minus 5, x is equal to minus 2, x is equal to minus 1, then x is equal to plus 1, x is equal to minus 3, x is equal to plus 3, and x is equal to plus 7. We have the solutions. And yes, and you see this denominator portion, hmm, this denominator portion x plus 5, this expression, it should be a square. Oh sorry, 1 x plus 5 has been cancelled, that's why we didn't have this x plus 5. Hmm. So it should be to the power of 4. So over here you see this is a positive quantity, a square quantity, and this is a also positive quantity. Fine. So 72 has been already there. Forget about it. Now forget about this expression. You see this 72, even if this is a positive quantity. Hmm. Forget about it. Now you see this expression. Look at this expression on the neighbor left side of this minus 5. On the left side of this minus 5, suppose maybe at x is equal to minus 5.1. Okay, at x is equal to minus 5.1, this is a negative quantity, this is a negative quantity, this is a negative quantity, even this is a negative quantity, this is a negative quantity, and this is a negative quantity. So altogether we can say that this f dash x would be a uh, sorry, I forgot to, I deleted this negative sign by chance. A negative sign was there. Hmm? So altogether, all these negative, negative 6 negative quantities were there. So all these 6 negative quantities would together form a positive quantity. Hmm? And this portion is a positive part, but due to presence of this negative part, we can say that f dash x is less than 0. F dash x dash, the derivative f dash x should be less than 0. So we can say that at x is equal to minus 5.1, that means on the left neighborhood of minus 5. Hmm. And what about x, the right neighborhood of minus 5? Suppose x is equal to minus 4.9. Okay, in very close to minus 5, you see this factor would be a positive factor and the remaining factors will all be negative. So the total expression, one positive and five negative factors. So this total expression would be a negative expression. Along with this negative expression, if you multiply by a minus sign, if we have a minus sign before this expression, in that case we can say that the function f dash x is greater than 0. So we can say that the derivative f dash would change its sign from negative to positive. So derivative changes its sign from negative to positive. And look at this picture. I told you that if derivative changes the sign from negative to positive, okay, then what we shall have, if derivative changes in sign, its sign from negative to positive, then we shall have a minimum value. Okay, so if you look at this book, if you look at this picture and look at this expression, so we can say that this at the point x is equal to minus 5, the function has a minimum value. In this way, you need to conclude that the function has a minimum value or maximum value. Now, if you consider one more point, I'm just discussing one more point and I'm leaving the similar conclusion for the remaining points for you as a homework. So, if you consider the point minus 2, you see in between minus 5 and minus 2, the function would have same kind of sign. But even if you want to check that x is equal to on the left of minus 2, minus 2.1, you can check that the point x is equal to minus 2.1, this would be a positive expression. This factor would be a negative expression and all the remaining factors would be negative expressions. So five negative factors, one positive factors, that means altogether a negative quantity. Altogether these six factors would give us a negative quantity, and along with that, if we have a negative sign, then we can say that similar to this expression, we can say that f dash x is greater than 0. So over here we have positive, f dash x becomes positive on the left neighborhood of the point x is equal to minus 2, and again at suppose right neighborhood of the point x is equal to minus 2, take a point x is equal to say minus 1.9, and then if you compute, what will you observe that at x is equal to minus 1.9, this is a positive factor, this factor would also be positive, and the remaining four factors would be negative. So four negative factors along with two positive factors, so altogether all these six factors would give us a positive quantity, and along with that one, if we have a negative sign before the positive quantity, then we can say that f dash x is less than 0. So what we observe over here, we observe that function changes, f dash x changes its sign from positive to negative. So we can write over here positive to negative. And in that case, as I told you earlier, that if we have this kind of symbol from positive to negative, if we have this type of result from positive to negative, if the derivative changes its sign from positive to negative, in that case the function would have a minimum value. Okay, so over here the function, sorry, minimum, not minimum, maximum value. So it should have a maximum value over here. So in this way we can discuss about the maximum and minimum value.